The last concept to talk about is stability. When we consider an RL or an RC circuit, the response is the sum of the natural and the forced response. That is, x of t is equal to x sub n, the natural response of t, and x sub f, the forced response of t. We can express this as x sub f plus the quantity x sub t naught plus x sub f e to the minus t naught quantity per tau, where x sub f is our forced response, i.e. if we have a voltage source or a current source, and x of t naught is our initial condition. Now, if our time constant is greater than 0, x of n approaches 0 as t tends to infinity, which leaves us with x of f of t, which is a stable configuration. That is, if our time constant tau is greater than 0, for any t within our system, we are going to have an equation that will tend to either 0 or a constant value. Now, if our time constant is less than 0, we have e to the minus quantity t minus t naught per tau, which would give us a positive exponent. And x sub n is going to tend toward infinity, which is an unstable configuration. That is, e to a positive quantity as a function of t will continually grow as t increases at an exponential rate. That is, our response of our system, either a voltage or a current, is going to exponentially grow. This is not stable. Thus, for our time constant to be greater than 0, we need RT times C or L per RT to be greater than 0. Since our capacitance and inductance are both positive quantities, this indicates that our resistance also has to be a positive quantity. Thus, these circuits are inherently stable if we properly do the mathematics. That is, our resistance, our capacitance, and our inductance are always going to be greater than 0.